All right, guys, in this video, we are going to complete the 5.1 section. In the last video, we talked about simplifying these trigonometric expressions using trig identities. In this section, we're going to be using that also to not just simplify, but actually go through and solve an entire equation. So you're going to see those identities used again, as well as just normal algebra. What I would say is if you have not watched the last video or if you missed that class, you definitely need to go back and watch that video before you watch this one, because some of those tricks are going to come in to play here as well. Okay. Also, for the on-level class, this is the only example that I'm going to go through for you guys. So if you just watch through this first example, you'll be set. The next one, we're going to let that be AP specific. So anyways, just to give you that idea, okay, or that heads up. That way we have more time to practice and stuff in class. Okay, so here, example 4. So to find all the values of x in our interval 0 to 2 pi, that solves this function. So you also will want to have your unit circle handy so that you can reference those values, since, you know, we're going to have to be actually solving and using some trig for that. So unit circle, keep your identities paper handy, and we'll be able to knock this guy out. Okay. First things first, looking at this problem, I would prefer, to me, it makes it a whole lot more clear to see fractions when they're actually written a value on top of another. So although it is workable, worth working it like this and seeing it this way, I just think it's so much more clear as to what's happening if I go ahead and stack them a little bit more. So I'm going to rewrite the problem. Okay, I'm going to write this as cosine cubed x, and this is over sine x. Okay, the other thing I'm going to do, since this is in terms of cosine and sine, the other thing I'm going to do is I'm going to go ahead and rewrite cotangent, because cotangent is cosine over sine. Again, that's one of our trig identities, that cotangent was cosine over sine. I am going to go ahead and rewrite that as well, and I'm going to also write that as a nice little fraction. So this is cosine x over sine x. And to me, I see this and immediately I'm like, oh, okay, so I can actually just set the numerators equal to each other, because if they're both over sine, right, it's the same idea as if you had, like, I don't know, if you had in an algebra problem, let's say you had x over 4 equals 3 over 4. Well, if you knew that, then that means x is 3. You can get rid of the denominators. It's just kind of like a logical thing. It's the same idea as multiplying both sides by 4. So you could view this as multiplying both sides by sine, and it cancels it out. But that becomes cosine cubed equals cosine of x. Okay. Now, there are a couple different ways that you can approach this from here. This is my suggestion, okay? I'm going to subtract cosine from both sides. If I subtract cosine of x on both sides, the main thing that you got to watch out for doing this is these two cosines don't combine. It's the same idea as if I had an x cubed minus x. They don't combine and make x squared. It doesn't work that way. So we're going to write these out separately. This is cosine cubed of x minus plain old cosine of x, but it's equal to 0. Now I could factor out a cosine. That's an option. Let's see where this leads me. Sometimes you just have to try stuff and be like, okay, well, this is an option. Does this get me anywhere? Okay, right there, I'm starting to see an identity I can use. Okay, I don't know if you guys have started picking up on this, but when you see a squared trig function with a 1 in it, then a lot of times you're able to end up using a Pythagorean identity. You just have to manipulate it a little bit first. The one I'm specifically thinking of is the first one. This is not already written as cosine minus 1, but I could rearrange it that way. So I'm going to do that over on this side just to kind of use some scratch paper, okay? So over in the margins, I'm going to look at that identity and see what I can do with it. Cosine squared theta plus sine squared theta equals 1. And I'm thinking, how can I write this as cosine squared minus 1? Because that's an option. I could subtract 1 here and subtract that sine squared. So that's gone and that's gone. That would give me cosine squared theta minus 1 equals negative sine squared theta. So if I use that property, I would be able to replace the cosine squared x minus 1. I can replace that with a negative sine squared theta. All right, so that's at least a little cleaner. Oh, we're with an x. Sorry, I started writing a theta. Do that all the time. Okay. All right, so here we go. These are our options, guys. We have two things that are being multiplied that equal 0, right? And so if I have two things that are multiplied to equal 0, then one of those things has to equal 0. That's the same logic that we used back in the day. If you had a problem where you said like x plus 2 times x minus 3 equals 0. What you would do is you would take each factor and you'd say x plus 2 equals 0, x minus 3 equals 0. We do that and you'd solve each, right? We're doing a similar idea. We have cosine times negative sine squared equals 0. So either cosine equals 0 or negative sine squared x equals 0. All right, let's go through and see what we've got going on here. Okay, I'm going to solve each one of these. So for the first one, I'm thinking, where is cosine going to be equal to 0? And specifically, remember the question, they gave us an interval from 0 to 2 pi. So I'm only looking at the values on the unit circle. I'm not looking at all the infinite places, okay? So where is cosine 0? I'm looking at where is my x-coordinate 0 on my unit circle. So I'm going to go on here and I'm going to look. Okay, x is 0 here at pi over 2 and also down here at 3 pi over 2. So my answers for this guy would be that x is either pi over 2 or 3 pi over 2. And those are the values within the interval. All right, so here negative sine squared x equals 0. Let's go through solving. If I divide through by a negative, that becomes sine squared x equals 0. If I square root both sides, then sine x equals 0. Now here's an issue. I don't know if you guys have identified this. You see how it says sine x equals 0. I want you to immediately jump back to your question. Sine x is not allowed to be 0. Do you see how in the original problem, sine is in the denominator? Sine can't be 0. So this will not result in an actual solution because sine cannot equal 0 based on the original problem. Okay, so here's a little reasoning for you to add to your notes in case you're just like looking back later and saying, what? How on earth did we get that? Couldn't we use it? Here's your little reasoning. Okay, I would make a note of it so that you can look back at that and it make more sense. All right, so guys, if you are in the on-level course, I would just say go ahead and stop the video here. You don't need to watch anymore unless you just want to. AP, stick around for one more just because there's a little bit of a trick in another question that you can sometimes use if the problems are kind of ugly. And so sometimes we're going to have some uglier problems. Anyways, awesome. On-level, click off, and AP, stick around. We're going to do one more. All right, example 5. Here we go. This question doesn't particularly look like it's worse than the other, but it is a little bit trickier as far as the factoring is concerned because on the last one, all I had to do is take out a greatest common factor. We took out the cosine. On this one, we have a little bit of a different situation because once I start trying to like clean this up, if I make it equal to 0, you're not going to have a sign in every single term. So let me show you what I'm talking about. Okay. To solve a problem like this, it's kind of in that quadratic form where you've got something squared, then you have the first power, then you don't have any signs, right? To be able to solve a question like this, I do need to try the same tactics that we use on a quadratic, meaning move the 1 over. So this would be 2 sine squared x plus sine x, and then subtract that 1, it's equal to 0. But this is what I'm saying. There is no greatest common factor for me to factor out like I had in example 4. And because of that, we're going to start thinking about how could I factor this and make it work. Now, you do not have to do this tactic or this strategy that I'm about to tell you. You can factor it and leave sign in the problem the whole time. However, not everybody has success with that because it does sometimes feel a little overwhelming. So here's what I'm going to give you a little, I don't know, maybe a little trick for. We're going to let sine of x, we're going to let that just be like a y or some other variable. Okay. Now, if you do that, here's what I'm dealing with. It would look like 2y squared plus y minus 1 equals 0. This is a little less imposing. This is something that might feel like it's a little bit more simple to solve. And then once you solve this for y, you can just plug the sign back into it, and it will feel, like I said, a little less overwhelming. Okay, so we do have to factor this. No, the factoring's not pretty on this, but we can deal with that. I do know that these first values have to multiply to be 2y, meaning one of these has to be y, the other has to be 2y. There's no way around it. All right, the last numbers have to multiply to be a -1, meaning that the values are 1, but we don't know which one's positive and which one is negative. That's what you got to play with for a second. So you're able to kind of narrow down how the factoring is going to work, but you may have to play with it for a second before you truly decide what's going to be positive and what's going to be negative. I'm going to bring my little erasable pen over here, and we'll use that to try to play with it. Okay, what if I made this positive and this one negative? Okay, if that's the case, then y times 2y squared, just like I want. Y times -1 would be a -1y, and then 1 times 2y is a positive 2y. So my question is, when I combine these, does that give me a positive y? -y plus 2y, yes, it does. All right, if that did not work, I would have swapped the signs and tried it again. But this does work out the way that it is, so I'm going to let that be my answer for my factoring. Let that be plus for this first one and minus for this guy. Okay? But like I said, sometimes you got to play with it, and if it doesn't work quite right the first time, then go back and try something different. All right, it's factored. Now remember how we said set each thing equal to 0. So I can have y plus 1 equals 0, or 2y minus 1 equals 0, y equals -1, 2y equals 1, y equals 1/2. Okay, but remember what we had said earlier. Sine is y. So I'm going to go back and I'm going to replace these y's with signs. I'm going to say sine of x equals -1. And I'm going to say sine of x equals 1/2. Now, I don't have any issues with what x can be here because my original problem, I did not have a fraction. I did not have anything that would have restricted that domain. So x can be anything I need it to be. Also, the question had said find all solutions to the trig equation. It didn't even box me into an interval. Like the last one had said it had to be from 0 to 2 pi. This says all solutions. So we're going to have to be able to represent our answer as all of the possible places for both of these things. So we're thinking, where is sine -1? Well, I'm going to look at my unit circle here. Where is sine -1? I want to know where my y is -1. So you can go all the way around the circle. Where are my y is -1? Oh, here they are at 3 pi over 2. Okay, so where is sine -1? That is if x had been 3 pi over 2. But here's the thing, that's not the only place. Every rotation after that also works. I'm just going to let this be for a second, but we'll have to do something more with that in a second because every single full rotation after that, every 2 pi after this or before it, is going to result in the same thing because they're coterminal angles. So let's also deal with this guy. Sine of x equals 1/2. Okay, well, where is sine equal to 1/2? You're going to go to your unit circle. You're going to say, where are my y values? 1/2. And there's no restriction on this, remember? So this is saying pi over 6 as well as 5 pi over 6. So here, x equals pi over 6 and 5 pi over 6. Okay? But again, it's not just these values, it's also all the coterminal angles. So I'm going to say as well as all coterminal angles. Okay? Which means I've got to find a way to express it. So here's what we're going to do. We're going to use big boy and girl notation. Okay? The way we're going to answer this is we're going to say x equals, for this first one, 3 pi over 2 plus, and remember how we said this is every single coterminal angle, which means every 2 pi, every interval of 2 pi, you're going to get this result. So we're going to say plus 2 pi times k. K is going to be just an integer to represent how many times you're going around the circle, okay? So that's one solution. Let's deal with these. Also pi over 6 plus, again, 2 pi k, because again, every single time you go around that circle, you're getting that coterminal angle. Then we're going to have one more, 5 pi over 6 plus 2 pi k. Now, I can't just leave it like this. I have to define what k is. So I'm going to say that k is an element of the set of integers. Now let me write that out so that you guys can understand what you wrote. This is part of set notation. I know it's been a while since you guys have seen this in your math class, okay? So this says k is an element of the set of integers. Okay, that's what this stuff means right there. Z represents the set of integers. This E, this weird looking E, is what we mean as it's an element of. Okay, so K is an element of the set of integers. It's just saying K is an integer, but it's the mathy way to do it instead of having to write out a sentence. Okay, so this is big boy and girl notation. We really should kind of get used to doing that because you know, being AP, this is supposed to be a college level course. So I figure it doesn't hurt us to see that. Okay, that is it, guys, for this video. So from here, I just need you guys to work on your assignments and message me if you have any questions. I'll see you later. Bye.